SwayamPrabha. Digital India. Educated India.
So students, we will be discussing today diffusion, and diffusion is an important aspects. But before I start that, let me just clarify a few things about the free energy composition diagrams which I have drawn in the last lecture for the peritectic system. See, this is the peritectic phase diagram on the right side. You see here there is a peritectic reaction, and that corresponds to a horizontal line or curve on the phase diagram, and the peritectic reaction is followed by an eutectic reaction here. So, you have alpha, beta, gamma, 3 solid phases and a liquid. So, as you clearly see here, at any temperature the free energy composition diagrams will have free energies of 4 phases: liquid, alpha, beta and gamma. So, at T1, which is at high temperatures above the melting temperature of the both the metals, you can see the liquid is this most stable phase. On the other hand, alpha, beta and gamma free energy curves are shown on the plot. At T2, that is on the peritectic isotherm, okay, that we referred as a TP in the drawings which I have drawn in the last lecture. As you see here, the gamma phase is not at all stable, that is why gamma is much above. On the other hand, at the peritectic isothermal, liquid, alpha and beta, all three are actually in in equilibrium or coexisting in equilibrium. So, therefore, there is a common tangent to all of them. That is what you clearly see here, there is a common tangent here. Common tangent means common tangent to 3 curves, okay. That means at the temperature T2, the gamma and the chemical potential of the alpha, liquid and beta are actually same. Similarly, at T3, T3 is its temperature little below the peritectic isotherm. At T2 you have alpha plus beta and liquid plus beta, and liquid are present. So, therefore, you can see here actually there are 2 tangents, clearly 2 tangents, one tangent between liquid and the alpha and beta, that is giving alpha and alpha plus beta region, then a tangent between beta and liquid, that gives you beta plus liquid and liquid, and in between the free energy of beta is the lowest. This is where actually there is some drawings were not clear, that is what I wanted to show you. So, at T4 basically again at T4 is what is the temperature above the eutectic temperature, which is additional temperature shown in this diagram. You can clearly see again it is alpha plus beta and beta plus liquid, but on the other hand, because at T4 you have a liquid plus gamma region, so there must be a common tangent between gamma and the liquid. That is what is shown here. This is the common tangent between gamma and liquid, okay. So, that is why liquid plus gamma and gamma both are actually phase field appear. So, this is the most complex one to draw. At T5, which is the eutectic isotherm, is or actually little below the eutectic isotherm rather, eutectic isotherm, not little below. So, there is a tangent between common tangent between beta, gamma and liquid, because at this temperature eutectic temperature 3 phases must be at equilibrium, okay. So, that is the difference you see here, and on the other left side it looks similar. So, left side curves actually similar at T5, T4 and T3, there is not much change. So, please make changes or try to be very clear about the things which I have drawn here and there, very clearly made to be understood. So, that is about the free energy composition diagrams. We will not go into details of the various other phase diagrams, but if time permits we can actually discuss case by case. So, as I said in the beginning of this lecture, we are going to discuss diffusion, and what is diffusion. So, as you see for the last whatever lectures, maybe I do not know 5 or 6 lectures which I have taken together, it is very clear that thermodynamics plays a role in dictating the equilibrium, in the sense what are the equilibrium phases will be appearing at a particular temperature pressure condition. But to achieve that equilibrium, system actually passes through many steps, and that is the subject of phase transformation. System can pass through a metastable equilibrium to a stable equilibrium. System can pass through from a unstable states to a stable state. So, whenever these things happens, that means whenever the phase transforms from one state to other state, it is important to know how long it takes and when the phase transformation will be half finished or quarter finished or even 10% of the phase transformation will over. These answers will come always from the diffusion, because diffusion talks about the atomic motion. Okay. So, I just discuss about basic concepts of diffusion, and I will just explain you how things happens. Okay, let me just close this one and open a new PPT presentations where things will be shown to you. As you know, diffusion is basically nothing but mass transport. Obviously, any phase transformations, if it is a diffusional actually, then it must be happening by transport of atoms from one phase to other phase. Like if liquid water is getting transformed to ice, so that means atoms or the molecules of water is getting transported from the liquid phase to the solid phase via an interface. Similarly, for metals, whenever you have a transformations, some solute or solvent it may be, you do not know which one is the pieces involved, will be moving from one phase to other phase. That is what is known as transport. Now, in gases and liquids, obviously motions of liquid atoms are actually random, and we always tell it is basically Brownian motion, because atoms can jump and collide and move. But in solids, diffusion happens or transport happens not by Brownian motions, but we will see in few minutes now vacancies and interstitial. Okay, so that is the most important things which you will be taught, because we are dealing with specifically more solid to solid transformations and a bit of liquid to solid transformations. So, the transport of atoms from one solid phase to other solid phase, it basically happens by vacancy or interstitial diffusion. Okay. So, that is very important. Now, you know, diffusion is very important, many things which happens in the surrounding as well as in our engineering field. Like, you know, as you know, if you are hungry and you buy pizza from some store, and then once you keep the pizza at the corner of a room, the whole room will be filled up with the smell. That is basically gas molecules transports very fast, because they are getting transported via Brownian motion by collision with each other. Okay. Similarly, deflation of a balloon, the balloon actually gets deflated because the molecule or the gaseous molecule gets transported via from inside the balloon to outside. Similarly, if you are using bicycle or motorcycles, you know, if the moment you open the tire, the knob, the air leaks out from the tires. That means there is a transport of molecules. Not only that, there is another important example which is in the used in the medicinal industry, is basically known as transdermal patch. This is the patch which many of the patients use to keep the things to the body part warm. Okay, that is very important. What is that? You see here there is a skin. There is a skin here, and skin actually is covered with a patch, and this patch has a medicine inside it. So, if you keep it, the medicine, slowly medicine will diffuse to the skin, correct, because this membrane which is put above the skin is basically porous. This is the way we can actually locally transfuse some medicine into the body. So, this is nothing but a diffusion of a, here it is a liquid, because medicines will be in liquid form, and it will be transported via this membrane into the body. So, but in the industry there are many. See, the carburation of steel, which you may not be knowing, but this is a widely used technique to make the gear teeth harder. Normally gear teeth are actually, after it is made, after machined out, it normally will not be hard enough to resist the wear and tear during the motion. So, to make it harder, we normally inject a lot of carbon inside this, so that some hard phases form, and this is done by putting these gears inside a furnace at high temperatures, where the carbonaceous gas is present, and the gas, from the gas carbon gets deposited onto these gear surface, and then that slowly diffuses inside it. So, this is another example, and this is what is shown here. This is known as case hardening in the industry, because case is outside layer. Okay, this is a section of the teeth. It is taken from the Callister books. You see here, elementary books available anywhere in the internet. So, these are the teeth. As you can clearly see, there is a thick black layer around it. This layer is formed because of the carbon diffusion from the surface to inside, and because of this diffusion of carbon, some hard phases will form. That's for that you need to know a little bit of steel metallurgy, which will be taught later, and these hard phases will protect these teeth to withstand the severe atmosphere of wear, tear, or even corrosive atmosphere. So, obviously carbon here is interstitial elements. It is not a which will be diffusing inside the iron lattice, because this is a steel piece. So, diffusion in solids, diffusion actually happen in solids, okay. But most of the discussions which we will be doing here, it will be basically based on the diffusion in solids, and diffusion in solids basically deals with movement of atoms to a solid medium. So, these atoms can either into the solid medium or from a gas or liquid or solid. That is what I given an example of a atom diffusing from gas, because in a carburizing we are keeping a carbon dioxide or carbon monoxide gas at a high temperature in which the gears actually kept. So, therefore, from the gas, carbon actually slowly diffuses into the solid steel. So, it also can happen liquid, because liquid phase carburizing or liquid phase nitriding is also there existing. Or I have given an example of a transdermal patch in which liquid medicine is slowly diffusing into the body. So, it is possible. Now, before we go into the various approaches of the diffusion, let me just tell you that why the diffusion actually happen. Okay, the reason for diffusion happening is basically thermodynamics. Okay. So, in the next few minutes we are going to spend time to explain you how diffusion actually happens and what is the basic reasons for diffusion to happen. So, I will go to the board and draw a few pictures. Let us suppose I just take two pieces of metal, okay, or two pieces of alloy actually. Okay, let me check for two color chalks, otherwise it will be difficult for you to see it. So, if I take two pieces of alloy, one piece is like this and other piece is like that. Okay. So, let us suppose this is A, this is B, and this is welded here. That is why there is a white and a pink color line. So, this is welded. Now, I take these these two joint pieces at a high temperature. So, the moment I keep it at high temperatures, atoms here will diffuse this, similarly atoms here will diffuse to this, because there is a compositional difference. Okay. So, obviously diffusion will happen through this interface, because the composition of A in the A is different than the composition in B. So, because of that there is a gradient automatically. No, but this gradient is obviously in a very macroscopic sense the responsible for the diffusion to happen, but that is not the main reason. Main reason for diffusion happening is the thermodynamics. Now, if I simply draw a free energy composition diagram, okay, similar to the ones which I have drawn in the lectures previously, and let us suppose this is the free energy composition diagram, free energy of the phase which is present in both the alloys, okay, both the pieces, and this is suppose G of alpha. Am I clear? So, that is the free energy composition diagram of the because it is the same alloy, little bit composition differences are there. Suppose this is steel only, carbon concentration is different from here to there. So, therefore, the free energy composition curves will be only one. Now, if I mark the compositions here, let me just mark by white line, composition here, composition there for A and B. Suppose this is A metal composition or B piece composition. Okay. Now, obviously, the free energies of these solutions are marked by these 2 points. Now, it is very clear the average free energy of the system will be somewhere lying there, right, because we have joined them together. This is the average free energy of the system. Am I clear? That is what it looks like. So, because of the average free energy is much higher, actually quite higher than the free energy of the system at this composition. You see here, this is the average free energy of P and B. So, because of that, the system can reduce the free energy by again going like this way. That means what? System can actually, atoms can diffuse from A to B or B to A. That is what it is. So, therefore, there is a thermodynamic driving force for the diffusion to happen, and this is very evident. This thermodynamic driving force tells you diffusion will happen at down the compositional gradient. Composition, if some suppose element is higher here, lower there, that element will diffuse from A to B. So, when it goes from A to B, so therefore, the compositions of the A will change, composition of B will also change, and because of that free energy of the system will reduce. So, that is the main reasons why thermodynamically things happens this way. Now, one can actually explain also using many others. Okay, let me draw it here. You can explain even using chemical potentials. That is not a big deal. Chemical potential I have already taught you. So, if I draw these curves, again I can actually explain easily. This is G alpha. Okay. So, if I draw the tangents here, let us draw with a different color. Okay, this was corresponding to alloy A, corresponding to alloy B. So, so therefore, it says you this is the chemical potential of component A at corresponding to alloy A, chemical potential of B corresponding to alloy A. Okay. Am I clear? Similarly, if I draw the another tangent here, okay, so it will go down, does not matter. So, this will be chemical potential of A in alloy B, chemical potential of B in alloy B. So, as you clearly see, there is a chemical potential gradient. Even if I look at the pure A end, that is the component suppose A in the alloy A and alloy B, there is a change of chemical potential. So, that means because of these difference of chemical potential, there is a delta mu here, there is a delta mu there, and this delta mu, which is the chemical potential difference, will drive the systems to equilibrate or the drive the systems to produce to have a atomic mass transports, correct. But it is true that here the diffusion happening down the concentration gradient, but it may not be the case always. In this case, it is very clear the diffusion happening down the concentration gradient. A will try to reduce its chemical potential from here to there, B will try to reduce chemical potential from here to there. Okay. So, that is what it is. In order to do that, they are actually diffusing in the down the concentration gradient. So, elements here will diffuse in this, elements there will diffuse in this. Okay. So, that is what actually happens in a normal situation, but you can also have abnormal situation. Okay. It just looks like abnormal, but it may not be abnormal situation. What will happen? Suppose if my free energy curves looks little bit awkward, okay, a little bit different. If it is like this, or let us draw it the way it is there in the suppose if free energy curves looks like this. Okay, so now how it will happen? And okay, let us first show it there. I will erase it up. And suppose I am here A and B, similar to this. This is composition of the alloy A, composition of alloy B of the any component B suppose. So, average is somewhere there, G average. So, as you can clearly see, this system can drop the free energy by doing that, still drop the free energy by doing that, still drop the free energy by doing that. Okay. So, from here I can drop the free energy extensively, very large content. Why? Because I can actually reduce the free energy systems. If free energy system was somewhere there at the beginning, now the free energy system can go down from here to there, there to there to there, okay, to the inflection point here, where there is inflection point obviously because there is a slope change. So, what is happening here? Very clearly, atomic pieces in the alloy A should have gone to B, and B in the atomic pieces in the B, which is rich in B, should have gone to A, but it is not happening. It is happening other way. This composition is in A composition in the alloy A. You see, this is richer in A. This is the composition at the beginning. This is richer in B. This is again more richer in A because you are close to A end. This is again more rich in A. This is more rich in B. So that means what? We are slowly diffusing. The atomic pieces are diffusing in the regions which is A rich and which is B rich. That means it is not happening down the concentration gradient. It is rather happening up the concentration gradient. Instead of making it more equilibrium like here or more at the center of this composition axis, where the things diffuse from here and things diffuse from there and they make it uniform, that is why you can reduce the free energy. It is happening other way. Compositions are actually going far away from each other. So that is what is known as diffusion above the concentration gradient or uphill diffusion. That is what we always call. This is downhill diffusion. Downhill means down the hill, okay, and this is uphill diffusion. If you draw the free energy composition diagrams, which I should not do it, okay, because if I do everything in the class, then you will not read. You can do a similar construction here on these points. Do it, okay. You can draw this free energy composition diagram here and there. You will clearly see diffusion happens down the chemical potential gradient. So that means what? The chemical potential gradient is what dictates you the diffusion. It is not the compositional difference. Composition difference we all perceive. Suppose if I drop a simple drop of ink into water, so you will clearly see after a few minutes ink will disperse into liquid water nicely. That is what is downhill diffusion, which we are all used to know. We all used to know this fact that if there is a high concentration region, atomic pieces will diffuse from the high concentration region to the low concentration region. We are not used to things like this, where a system is behaving in the opposite directions. That is, atomic pieces are actually diffusing above the compositional gradient. Okay. The pieces in the alloy A is becoming rich in A, pieces in the alloy B is becoming rich in B, which is something which is difficult to understand or difficult to believe. But this happens because of thermodynamics. Because of the free energy curve, it happens. Very simply, why it happens? Because there is immiscibility. We know that this kind of nature of free energy curves lead to immiscibility in the systems. That means delta H is positive and very high. Because delta H is positive, or rather enthalpy of mixing is positive of the system and high, then atoms actually will not like to stay together. A and B will like to go away from each other because their bond energies are higher. AB bond energies are much higher than A and BB bond energies. So system will not like to form AB bonds. System will like to be staying with AA bond and BB bonds. That is why this kind of free energy curves appear in the system. We have already discussed about quasi-chemical theory and told you the reasons for having such kind of free energy curves. So the moment you have such a kind of free energy curves, your behavior will be different. But remember, it is this chemical potential gradient there also, here also, which dictates you the diffusion directions. The free energy, basically this is the main aspect. The change of the chemical potential always dictates you the diffusion directions. This is not I want you to understand very clearly, because most of us has a concept that is the compositional difference which dictates the diffusion directions. No, it is this chemical potential difference. That is what tells you why these things will happen. Okay, so by now you could have understood, you could have learned how to draw these diagrams. So let me just draw it here. So as you can clearly see, it has to be drawn in a very big way, otherwise things will not be clear. So if I draw, it will be going there, it will be going there. Similarly, if you draw here, okay. So you can clearly see this is your A chemical potential of A in the alloy A, correct. This is the chemical potential of B in the alloy B, and these ones where it will meet, this will be chemical potential of A in alloy B, because this is where it meeting, this is chemical potential of B in the alloy A. So you can clearly see there is a gradient. So A will go to A, B will go to B. There is a huge change of chemical potential. This is B in A. So all the atoms which are there, B atoms which are there in the A will slowly go into B. All the atoms which are present in B, A atom present in the B alloy will slowly go into A alloy. That is how actually happens. So therefore this large change of the chemical potential is what is dictating your diffusion direction. So diffusion happening down the chemical gradient, but it is happening up the concentration gradient. So therefore thermodynamics is not failing here. Thermodynamics is giving us the real answer why diffusion happens inside the systems above the concentration gradient, or afield diffusion happens. So that means the basic driving force for the diffusion to take place is basically the chemical potential gradient. It is the chemical potential gradient which gives you the direction of diffusion, and in fact it does not tell you how fast the diffusion will happen, how slow that happens. That will be decided by the other aspects. Let me be very clear about it. Okay, so please keep this in mind, because in the course we are going to discuss various aspects of the rate of transformations, and diffusion is going to come into picture. So thermodynamically this is what actually explanation for diffusions. Now we will see how kinetically we can explain in the next lecture.